Okay, we are recording and you should be able to see my screen now. Good. Okay, so in this video, I just want to talk a little bit about the limit comparison test. So this isn't a test that we're required to know in 10B, but it is a test that proves to be really useful in some cases. And you are allowed to use it, but you need to use it correctly with full rigor to get full credit on an FA. So I just want to go through maybe a little bit about why the limit comparison test and then do a couple of examples. So before we begin, let's recall from 10A. How do we find horizontal asymptotes? So we have to, in order to do this, we have to take the limit of the function f of x as x goes off to infinity. Okay, and if this limit was some finite number L, then that meant that the function had a horizontal asymptote as x goes off to infinity at L. Okay, so let's do an example of this. So we're going to find the horizontal asymptote for this function x squared plus 3 over 2x squared plus 1. So to do this, well, we have to take the limit as x goes to infinity of this quotient here, right? Now, so there's a couple ways to do this. So one way is to look at dominating powers, the leading term of the, the coefficients of the term with the highest exponent. But essentially, with full rigor here, in order to evaluate this limit, we would have to do L'Hopital's rule 2 times, right? But it turns out that this limit is just 1/2 after doing L'Hopital's rule twice. Okay, so that means that this function has a horizontal asymptote at 1/2, right? But let's go a little bit deeper than just that. Okay, so what does that mean? As x gets really big, that means that this function on the top here, this function, as x gets really big, is roughly half the size of this function. Okay, so as x gets really big, x squared plus 3 is approximately equal to 1/2 times 2x squared plus 1. And that kind of looks like it makes sense, right? Because look, when you have $1 billion and you go spend $3 on a pack of gum, you're still a billionaire, right? So as x gets really big, this 3 doesn't really matter. Same thing over here, as x gets really big, this 1 over here doesn't really matter, right? So then you have x squared is about half of 2x squared, and that makes sense, right? So what is this telling us? It says that x squared plus 3, intuitively, it's saying that it's growing, it grows half as fast as 2x squared plus 1. Okay, that's what it's saying. So x squared plus 3 grows half as fast as 2x squared plus 1. Good. So now we're about, 5 minutes into this video, and I have yet to talk about a series, right? So what does any of this have to do with sequences and series? So let's talk about series. We can translate this exact idea in terms of series, okay? So the first thing we're going to do is consider the sum from n equals 1 to infinity of 1 over 2 n squared minus 1, okay? So intuitively, we should look at this and say, okay, what happens when n gets really, really big? When n gets really big, well, this minus 1 here, that's not going to really make a difference, right? What's going to make a difference is only what's going on here. So as n gets really big, this looks, n grows, which is the important thing right here. And we'll talk about this in a little bit. This looks, n grows like 1 over, n squared. Well, really 1/2, right, of this. So 1/2 times 1 over n squared. Let me zoom in here. Sorry about that. 1 over n squared. Okay. So this, as n gets really big, we can forget about the minus 1, and it looks like 1 over 2n squared, which is just 1/2 times the sum of 1 over n squared. And we know that this converges, so that should tell us something about this, okay? And now we can actually use a direct comparison test, but sometimes the algebra gets a little bit fussy to do the direct comparison test. So oftentimes it's actually a lot cleaner to use the limit comparison test. So our gut should say that our original sum here, 1 over 2n squared minus 1, our gut should say that it converges because it looks and grows like a sum that we know converges. And we know that the sum of 1 over n squared converges because it's a p-series with p equal to 2, okay? So this is how we should be feeling. And now let's prove it using more rigorous math. So in order to do that, we want to look at how one grows with respect to the other one, okay? So just like horizontal asymptotes, we want to take this, our original series here, and we want to take that as the numerator of our fraction, and we want to compare it to this 1 over n squared term over here, and we'll put that in the denominator. Then when we take a limit, we could look at how this, our original series, grows, the terms of the original, the summands of the original series grow with respect to the summands of this new series. Okay, so let's go ahead and do that. So in order to do that, we're looking for the limit as n goes to infinity of 1 over 2n squared minus 1 divided by 1 over n squared, right? So this turns into 1 over 2n squared minus 1 times n squared over 1, which becomes the limit as n goes to infinity of n squared over 2n squared minus 1, which we know to be 1/2 after doing L'Hopital's rule twice. Okay, good. So what does that mean? That means that for big N, when n gets really big, 1 over 2n squared is approximately half of 1 over n squared. Okay, so in this case, it actually turns out that 1 over 2n squared minus 1 is going to be smaller than 1 over n squared when n gets really big, right? So since sum of 1 over n squared converges, since it's a p-series with p equal 2, then that means that the sum of 1 over n, 2n squared also converges, right? Because this is a finite number, and this sum is just some constant multiple. When n gets really big, each summand is just some constant multiple of each summand in this sum. And when I add together all of these, I get a finite number. So this is just a constant multiple times some finite number, which is also a finite number. It didn't really matter that this is 1/2. It could have been 1,000,000. Okay, it could have been 10 million, whatever, it doesn't matter. The key thing is that 10 million times a finite number is still a finite number. Okay, so this is the idea behind the limit comparison test. So let me just go ahead and state the limit comparison test. So we need that an and bn are two non-negative sequences, okay? So that means that each term an and also bn is bigger than or equal to 0 for every n in the sequence. So the limit comparison test says the following. If I take the limit as n goes to infinity of an over bn, and I get some number L that isn't 0, okay, so this is a finite number that's not 0, then both the sum of the ANs and the sum of the BNs converge. So they either both converge or they both diverge, okay? So this is essentially saying that it's really important for us to pick our sequence BN so that we know that it converges or diverges. Because if we don't know whether or not BN converges or diverges, then we can't conclude anything about AN, okay? So let's look at what it says next. If the limit of AN over BN is 0 and the series of BNs converges, then the series of AN converges. Okay, so let's think about what this one's saying. In order for this to be 0, in order for this to be 0, that means that Bn has to grow a lot faster than An, right? Because it's a fraction. So the bottom needs to get really big, a lot bigger than the top quickly. So Bn grows a lot faster than An. So what this theorem is saying is that if the one that grows really fast is finite, if it converges, then the one that grows slower also converges. Okay, so let's think about what would happen if Bn didn't converge. Then all this is saying is that An grows slower than something that grows really fast and diverges. So that doesn't really allow us to conclude much about An, right? So that's kind of like saying that, that's kind of like when in the comparison test when we would say the sum of the A, if you had a series that was smaller than a divergent series, then we can't conclude anything about the smaller series. That's the same exact thing that's going on here in statement 2. And I'll do an example in a little bit. Finally, the last statement is part 3, that says that if the limit as n goes to infinity of An over Bn is infinity, and Bn diverges, then An also diverges, okay? So what this is saying is that if An grows faster than Bn, and the sum of the slower one is infinite, the slower growing one is infinite, then the sum of the faster growing one will also be infinite. So this should also parallel the comparison test in that if the smaller sum diverges, then the bigger sum also diverges. Okay, so this is very similar to the direct comparison test. Okay, so let me do a couple of examples here. So let's take the sum 1 over n squared. Okay, so we already know what happens here, right? It converges because it's a p-series. But now let me compare 1 over n squared to 1 over n. Okay, so I'm going to compare it to 1 over n. So this is my An, and my Bn is 1 over n. So over here I have limit as n goes to infinity of An over Bn. And this is the limit as n goes to infinity of n over n squared, which is the limit as n goes to infinity of 1 over n, which is 0. And therefore, by the comparison test, since it's some finite number, 0, and I know that 1 over n diverges, then that must mean 1 over n squared diverges. But wait a minute, I thought we just said that 1 over n squared converges. What did we do wrong? Well, this is exactly what case 2 is saying, right? We look at the hypotheses in case 2. Our limit is 0. Look, our limit is 0. That means we're in case 2. In order for us to be able to say anything about An, we need that Bn converges, okay? And in this case, Bn is 1 over n, and we know that the sum 1 over n goes from 1 to infinity, diverges because it's harmonic. So this means this entire analysis that we just did says that we can't conclude anything. Using the limit comparison test. But with that being said, we don't really need the limit comparison test. We know that the sum of 1 over n squared converges. Okay, so let me give you an example of why we need Bn to be divergent for part 3. Okay, so my next example is the sum 1 goes to infinity of n cubed. Okay, so this clearly diverges by the divergence test. Okay, but let's take Bn, oops, I write in blue, but let's take Bn to be 1 over n squared, okay? So we know that the sum of Bn converges, right? This is p series with p equals 2. So we know it converges. So let's do the comparison. So what we get here, if we take An over Bn, we get the limit as n goes to infinity of n cubed times n squared, which is, this is n to the 5th, and we know that this limit is, I'll put in quotes, infinity. Even though, I mean, it is infinity, right? So take the quotes away. Okay, so we know that limit's infinity. It diverges, it goes off to infinity. Now, according to part 3, if this is the case and Bn diverges, then An diverges, okay? But what we have for Bn, we have a sum that converges, right? It's the sum of 1 over n squared. So this test says that we can't say anything. Because the sum of the Bn's converges. But like I said before, that doesn't really matter. We don't need a limit comparison test in this case because we already know the sum of n cubed diverges by the divergence test. Okay, so let me give an example where the limit comparison test is actually useful. So let's take something like the sum n equals 1 to infinity of n squared plus 2n divided by n cubed plus 3n plus 1. Okay, so we can do a direct comparison. That would be fine, but there's some algebraic hoops that we would have to jump through, okay? So let's see what our intuition tells us. As n gets really, really big, okay, we don't really care about the 2n anymore. We don't really care about the 3n plus 1. So for big N, the an is of the form n squared over n cubed, which after simplifying is 1 over n. Okay, so when n is really big, this sum is kind of similar to 1 over n, right? So our intuition should suggest that this sum should diverge. Okay. Now, our intuition, so that's great. So we have an intuition, and we want to try to figure out, like, you know, whether this sum converges or diverges, and we have a guess that it diverges, and that's a fantastic first step. But the little analysis that we just did, looking at what an actually looks like for really big N, also gives us a candidate to compare our original series to. Okay, so let's do the limit comparison test, and we're going to compare it to how this thing acts when n is really big. So this will be our an, and this over here will be our bn. So the limit becomes n squared plus 2n over n cubed plus 3n plus 1 divided by 1 over n, which is the same thing as times n over 1. Okay, so that's equal to the limit as n goes to infinity of n cubed plus 2n squared over n cubed plus 3n plus 1. And then we do L'Hopital's rule 3 times, or we could just look at the dominating powers and see that this limit is equal to 1. Great. So we're in case 1 of the limit comparison test. We took the ratio and we said, oh, look, the limit is L, and L is not 0. So 1, in our case, is playing the role of L. Then both of them converge or both of them diverge. Okay, so since this limit is 1, by the limit comparison test, since the sum n equals 1 to infinity of the bn's, which are 1 over n, diverges, so does the original sum. Great. So one thing I want to point out here is that the intuition is great. You can look at this and say, for big N, this is going to grow like 1 over n, okay? that's a great place to start. But in order to earn credit on the FA, it can't end there. You need to go through the steps and say, I'm going to compare this to 1 over n, take the limit as n goes to infinity of the quotient an divided by bn, actually take that limit, show that it's equal to some finite number, and then you can apply the statement of the theorem.